Okie dokie, here is how to answer the elastic potential energy questions. So, having a quick read of this question, it says calculate the elastic potential energy of a spring with spring constant 20 newtons per metre, which is extended by 0.2 metres. So first job is to write down the equation. Now you are given this in the exam. It's on the equation sheet, so it's a case of getting used to spotting it and using it. It says half times the spring constant K times the extension squared. Now actually that could be compression, as we're going to see in a later question just over here. As long as they, however, the springs follow Hooke's law. Now this is going to be something that we cover in the forces topic, so if you're watching this in the energy topic when we introduce this for the first time, you won't know much about Hooke's law. You might have done a little bit earlier on in school and in previous years, but you won't know too much about it. So we'll come to that later. So let's now substitute the numbers in. The elastic potential energy we don't have, so rewrite E. Half is a constant, it's just always there. 20 is the spring constant and the extension is 0.2. Don't forget the squared. First job is to do the squared bit when we're simplifying. So it is E equals half times 20 times 0.04. That is what 0.2 squared is. Okay. So then we can simplify it. So then we just solve the question. Stick that into the calculator. 0.04 times 20 times 0.5, which is a half, equals 0.4 joules. That's how much energy is stored there. Okay, on to the next one now. Calculate the elastic potential energy of a spring of spring constant 12 newtons per metre compressed by 0.05. Like I said earlier, compression in this case will replace extension. Same thing. Write the equation down. We don't have E. So half times 12 times 0.05 squared. Simplified gets us half times 12 times 0.0025. And then again, we just dump that all into the calculator. So times that by 12 times by 0.5 gets us 0.015 joules of energy. Okay, we're on now to calculating the spring constant this time. So now we have an equation that we are going to have to rearrange. So let's dump the numbers in. We have the energy there, which is 5,000, equals a half times the spring constant, which I don't know, times the extension, which is 4 meters squared. Again, we simplify. 5,000 equals, or we'll do this one first, 4 squared is 4 times 4, which is 16. Now half and 16, we can simplify that further. Half of 16 is 8, 8 times k. We now need to get rid of times k to leave times 8 to leave k on its own. So we do the opposite and divide 8 on the other side of the equation. That cancels that out. And we have k equals 625 newtons per metre. Final one. And this is one that is now very similar to a rearrangement that we do with kinetic energy, because essentially the equation follows a similar sort of format. E equals half times k, in kinetic energy it's mass, times E squared. In kinetic energy it's V squared for speed. And in this case we're going to have to find E. So let's dump the numbers into, extension, the small e. So let's dump the numbers in. 10,000 joules there, times a half, times the spring constant, which I'm given, which is 50, times E squared. Here we're going to simplify. So 10,000 equals half times 50, which is 25, times E squared. Now, we're going to leave E squared on its own first. We're going to get rid of times 20, divide 25. Sorry, get rid of times 25. And that cancels that out. We are now 400 equals e squared. Now, as with everything like we've seen just here, when we have times 25, we do the opposite and divide by 25. If we had something on the bottom and it was currently dividing by a number, we would times it to get onto the other side. We always do the opposite. So the question here is, what is the opposite of square e squared? What's the opposite of squared? How do we get rid of that to cancel it out? Well, the opposite of squared is a square root, and that then cancels that. So the square root of 400 is 20. Work backwards, 20 times 20 equals 400. So 20 metres.